In this video, we're going to look at operations with algebraic vectors. So since all vectors can be expressed in terms of unit vectors, all the rules of vector algebra apply to algebraic vectors. So if we have ordered pair notation, and we have a1, b1 plus a2, b2, we just add the x components, and then we add the y components. In unit vector notation, we're going to add the x scalars. So the x scalars are right here, and then we're going to add the y scalars right there. Okay, you can see x scalars are added, and y scalars are added right there. So for vector u equal to 3, comma, -6, and vector v equal to -5, comma 2, find vector w, which is equal to 6u minus 3v. Okay, so we're going to start off by just restating the question. So vector w is equal to 6u minus 3v. And now I'm going to sub in u and v. Okay, so subbing in u as 3, -6 and v as -5, 2, we can see that the scalar of 6 multiplies to the 3 and then multiplies to the -6. And the scalar of -3 is going to multiply to the -5 and then to the 2. So I end up with vector w is equal to 18, comma, -36 plus 15, comma, -6. And now I just add the x components and the y components. So 18 plus 15 is 33, and -36 plus -6 is -42. Okay, so that was a pretty straightforward example. This one's a little bit more challenging. If D and E are points in space, find the vector that connects those 2 points. So these are points in space, but we can make position vectors out of them by taking a tail at the origin to D and a tail at the origin to E. All right. And so if I do that, I can create the position vectors OD and DE. Okay, so if I add OD and OE, do they make DE? Well, as you can see here, the tip of this one right here does not align with the tail of the next one. So this does not equal to DE. So how can I rearrange these position vectors so that they can make DE? Well, if I flip the order of O and D, so if I have DO plus OE, that should be equal to DE. Well, how do you flip the order of OD? Well, you apply a negative in front. So applying a negative in front of OD would cause me to flip the order, and then I would have DO plus OE, and that should be equal to DE. And starting with a negative can be a bit jarring, so let's just rearrange it. So OE minus OD is equal to DE. And so we can come up with a general rule here. So any vector that we want to create with 2 points in space, we can say the final position vector, OE, minus the initial position vector, OD, will give me the vector between those 2 points in 3 space. So therefore, any vector is equal to the final position vector minus the initial position vector. So final position vector minus initial position vector is equal to a vector in space. Okay, so let's sub these in. OE is -2, 4, 1, and OD is 4, 5, -7, and that should equal DE. So final minus initial is equal to the vector DE. And so again, we just have to now subtract components. -2 minus 4, 4 minus 5, 1 minus -7. So -6, -1, 8 is equal to vector DE. Okay, so for parallelogram A, B, C, D, 3 vertices are A, 1, -5, 2, B, -3, 4, 4, and C, 5, 8, 10. Find vertex D. Okay, so what I'm going to do is I'm going to assign corners of this parallelogram A, B, C, and D. Okay, and I don't know what vector D is, so I'm going to label that X, Y, or point D. I'm going to label that X, Y, Z. And then I'm going to write a let statement that let x, y, z represent point D. Okay, now what I'll do is I'll create vector AB. So what I mean by vector AB is if I took a vector from A to B and I just placed it right there, and I'll make that a little bit thicker so you guys can see it. There we go, vector AB. Well, you can see that vector AB should then be equal to DC if this is a parallelogram. Okay, so how do I find vector AB? Well, this is just what we said from before. If I want to find a vector AB, I'm going to do final minus initial of the position vectors. So OB minus OA if I want to find vector AB. So OB, the origin to B, would be -3, 4, 4, and the origin to vector A would be 1, -5, and 2. So you can see final minus initial, and then I just subtract the components. So vector AB is equal to -4, 9, and 2. And as I said before, AB has to be equal to DC. They point in the same direction, and they also should have the same magnitude if it is a parallelogram. So vector AB is equal to vector DC. Now, how do I find vector DC? Well, it's the same as before. Final position vector minus initial position vector. DC is just equal to vector OC minus vector OD. So DC is equal to 5, 8, 10 minus X, Y, Z. And that's because point D I defined as X, Y, and Z. All right, so let's go ahead and subtract components of 5 minus X, 8 minus Y, 10 minus Z. Okay, so DC is given right here as 5 minus X, 8 minus Y, 10 minus Z. You might notice that AB right here, I'm just going to highlight it for us on the page, okay, is equal to -4, 9, and 2. And these two vectors have to be equal. So I'm actually just going to rewrite this, and I'm going to space it out so that you can see exactly what is equal. So as you can see, the X components have to be equal, the Y components have to be equal, and the Z components have to be equal if the two vectors are equal. So we can now generate 3 separate equations. So therefore 5 minus X is equal to -4, 8 minus Y has to be equal to 9, and 10 minus Z has to be equal to 2. And so I can rearrange now and solve for each of these variables. 9 is equal to X, -1 is equal to Y, and 8 is equal to Z. And so therefore point D is 9, -1, and 8. Okay, moving on. Using vectors, determine if A, 2, -9, B, 1, -6, and C, -3, 6 are collinear. Well, collinear means that they lie on the same line. Co, prefix meaning share, linear meaning line, so do these 3 points share the same line? If they lie on the same line, well, that would mean that so AB is just some scalar multiplier of BC. Okay, so I'll draw a diagram so you can see what I'm talking about. So if these points lie on the same line, then AB is going to be some vector multiplier of BC, or BC is some vector multiplier of AC. So some scalar multiple of, BC is some scalar multiple of AB. Okay, so what I'm trying to prove here is the following. I'm trying to prove that BC is some scalar multiplier of AB, which means it has to have the same direction to see if A, B, and C are collinear. Okay, so what I need to do is I need to find vector AB, and I find vector AB using position vectors. So vector AB is just OB minus OA. OB is 1, -6 minus OA 2, -9. So AB is -1, 3. Similarly, I have to do the same thing to find vector BC. So I'm going to say OC minus OB. So vector BC is equal to -3, 6 minus 1, -6, and vector BC is -4, 12. All right, so I need to take a look at this right here. I can see that to get BC, I can multiply AB times 4. So BC is just AB, but multiplied by 4. So therefore, BC is just 4AB. And so now I have proven that BC is just 4 times vector AB. And if BC is just 4 times vector AB, well then they have to point in the same direction. BC just has a larger magnitude, right? So these 3 points are in fact collinear. So therefore A, B, and C are all on the same line. Okay, next one. Vectors u and v are parallel. Determine the values of x and y given that u is 3, x minus 6, 7, and vector v is -6, 5, 8 minus 2y. Okay, so if these two vectors are parallel, then they have to point in the same direction. And if they're pointing in the same direction, that means that one is just a scalar multiplier of the other. So they're nearly equivalent vectors, but one is just a scalar multiplier of the other. So vector u is just some scalar multiplier of vector v if parallel. Okay, so let's actually use vector u and vector v in this equation. So I've written out my vector u is equal to k vector v. Well, k can distribute to each of these components. So I've distributed k to each of the components, and then I've color coordinated the x components, the y components, and the z components. So distributed the k in, and then coordinated the x components, y components, and z components. And the reason why I've done that is because now I can create equations for the x, for the y, and for the z. So let's just start with the x, the green ones. So therefore 3 is equal to -6k. And then rearranging, -3/6 is equal to k, which simplifies to -1/2 equal to k. All right, so I have my k value. Now I can solve for these unknowns, x and y. So let's take a look at the next set of equations, the red equations. So x minus 6 is equal to 5k. Great. Well, I know what k is, so I'm going to sub that in. X minus 6 is equal to 5 times -1/2. Let's isolate for x here. X is equal to -5/2 plus 6. Getting a common denominator, 6 is just 12/2. So x is equal to 7/2. So for the blue equation, it's going to be the same thing. We know what k is. We're just going to sub in the k value and solve for y. So I'll do that all in one step. So 7 is equal to k 8 minus 2y, subbing in the k value of -1/2, distributing it in, and then isolating for y. Okay, homework is listed here, and thanks for watching.